Hello, I am Gianluca Torta, and in this video, I will present you the connected autonomous vehicles use case of the MPAI organization. So first of all, what is a connected autonomous vehicle? It is a vehicle that has both autonomous driving capabilities and connectivity towards other entities. The main features of a CAV that make it useful are the following. It should be able, first of all, to understand the human utterances to get commands from humans. It should be able to do automatic planning of a route towards a destination, as well as, of course, continuously sensing and interpreting the environment in order to move safely into it. And since it is connected, be able to exchange information with other cars and entities to improve its performance, and finally to actually execute the planned actions by giving commands to the motion subsystem of the vehicle. So why it is interesting to standardize the CAV information technology components? Well, there are several reasons. One of the most important ones is that a CAV is made actually by very disparate technologies from the IT point of view, and such technologies should interoperate, and so would benefit greatly from standardization. Moreover, it is a delicate domain because CAVs can hurt people, and so they must be safe, reliable, and explainable. And this also can be improved by a standardization process that improves transparency. From the practical point of view, we foresee a big market for cars that makes them relevant, of course, also. And MPAI thinks it is in a good position for devising an effective CAV standard for, again, for several reasons. And mainly the CAV, at the core of a CAV is artificial intelligence for its autonomous decisions. And this is also the main focus of MPAI. Moreover, MPAI addresses many other applications, and some of them are relevant and can so be the results can be reused in the CAV standard. For example, when we think about audio and video. How does the top-level model that we have considered look for the CAV architecture? It is subdivided in 4 subsystems that more or less correspond to the characteristic that I mentioned before. The human CAV interaction for input-output with the human, the environment sensing subsystem for input from environment sensors, the core intelligence of the autonomous motion subsystems that must decide what to do, and finally the motion actuation subsystem that executes the commands in the real world. And don't forget that in all of these subsystems there is horizontally the need to standardize, to consider and standardize the communication aspect that is fundamental for CAVs. So now I would like to give you some details for each of the 4 subsystems. But instead of going through the lists that you have just seen passing in the previous slides, I will consider this reference model that is in the form of an AI workflow defined by the AI framework that is another standard of MPAI that you can, of course, find material about. And so I will comment on this graphical representation of the subsystem. So first of all, the the HCI must be able to separate the human from the rest of the cabin, let's say, and both the sound and the speech of the human from the sound and speech, from the sound of the environment, and the figure of the human, in particular the face and the gesture, as you can see here on the left. Once the speech has been in some way separated, it must be understood. But not only the text of the speech is important to understand, but also the emotions carried by the speech, as well as by the gesture and face. Pragmatically, what this leads to is the understanding of the intention that the question posed by the user carries towards the CAV. So the other important part of the HCI is the production of response from the CAV, in particularly in form of speech synthesis, but also materializing itself as an avatar with a face, with eyes and lips that all should move in sync and be consistent with the emotion of the speech, and gaze at the right person in the cabin, in case there are more than one. Okay, let's go to the second subsystem, the environment sensing subsystem. It is in some way, it is very important, but in some way looks simpler than the other one, because its main goal is to collect data, especially the data from visual data from the environment, like from radar, LiDAR, but also audio data, or cameras, and make a first interpretation of them in order to build what we call a basic word representation. That is an internal representation of the CAV of the surrounding environment, including what objects are there, how do they move, where they are, and so on. This is the main purpose of the ESS. So now let's go to the core of the CAV, the autonomous motion subsystem that talks to all the other subsystems. In particular, it must be able to receive commands from the HCI, and also to give back a representation of the internal representation of the world, so that the user can explore it. It gets from the ESS, it gets the basic word representation. The most important component is the one here that gets this basic word representation and fuses it with the other basic word representations coming from other CAVs in range, so that through connection, the connectivity of the CAV. And this can improve, of course, accuracy, but also the completeness, because some objects, for example, may not be seeable from the CAV at hand, but from another CAV that is better placed. So thanks to all these modules, after the planned route is then and thanks to the input given from the representation of the world FWR, the AMS is able to synthesize commands that are given to the motion actuation subsystem for actual execution. So let's go to the last subsystem, that is the motion actuation subsystem. Again, it has it provides some data about the mechanical status of the CAV, like the pose, velocity, and acceleration, that goes to the ESS to join the other data coming from the other sensors we have seen there. But the most important role is that of taking commands from the AMS, as we just saw, and interpret them because they are given at a certain abstract level. It must interpret them and turn them to low-level controllers of the electromechanical parts of the vehicle for actual execution. And these are like the wheel motor, wheel direction, brakes, and so on. And this in turn give feedback about the outcome that is not always what we expect. And this feedback is again interpreted by the MAS and given back to the it is interpreted by the MAS, the motion actuation subsystem, and given back to the autonomous motion subsystem in order to inform it about the status of the CAV. That is, of course, also very relevant for making decisions. So in summary, before concluding, I wanted to list a few technologies that would benefit from CAV standardization, but would also, of course, be very useful to define in first place, to define the standard in first place. For the human-CAV interaction, the most important ones are typically about the audio, like the speech and sound separation and the scene description from a 3D audio. I don't mention all of them, only the most important due to time restriction, but you can read them. And the environment sensing subsystem, of course, focuses instead on the visual scene that can be reconstructed from all the mentioned sensors like camera, LiDAR, and so on. The autonomous motion subsystem must have a very well-defined dialogue system with the HCI in order to produce command to get commands and produce responses to the user, and must be able to know the laws in the place where the car is, like traffic rules, and interpret the traffic signals in order to be effective in making decisions. Finally, the motion actuation subsystem must be able, of course, to have to interpret these high-level commands and give high-level feedback to the AMS. Okay, we are at the end of this presentation. If you want more details, you can go to this URL, cav.mpai.community. And I thank you for your attention. Bye-bye.